Up next, we have a circular motion one. So we have an object rotating in a circle with an acceleration of 7 meters per second squared. That's that centripetal acceleration, or the acceleration of an object going in a circle. And we want to know what the acceleration would be if the radius is doubled without changing the speed. So this is one where we're going to set up our original situation and our new. So in our original situation, we have our equation, centripetal acceleration is v squared over r. So I know that my acceleration is 7. So 7 is going to be equal to v squared divided by the radius of the circle. In my new situation, all right, I don't know my centripetal acceleration, so I'm just going to leave it as an a, and that's going to be equal to v squared divided by 2r, because it tells me that my radius is doubled. Lots of ways of solving this. I think the easy one in this case is to solve both equations for v squared. So we have 7r equals v squared and a times 2r equals v squared. And then we can just set those two equations equal to each other. So we have 7r equals a times 2r. Divide by r to cancel out the r on both sides, and then divide by 2. And I get that my acceleration is 3.5 meters per second squared. Answering to 2 sig figs, don't have to worry about rounding here, it's just 3.5 meters per second squared. We could also think about this logically. If we double that radius, okay, we're doubling something on the bottom of this fraction here, that's going to cut my acceleration in half because the radius and the acceleration are inversely related. Moving on to part B, I'm still going to have my original 7 equals v squared over r, and then I'm going to set up my new one when my speed is doubled. So I'm going to say that my acceleration is 2v, and remember it's that entire quantity squared, not just the v, so 2v squared over r. So that means my new situation is actually 4v squared, because we're squaring both over r. This one, to solve it, I'd actually use a slightly different technique. I'd look at this equation here, and I'm going to factor out a 4 here. So I'm going to say 4 times the quantity v squared over r is my new acceleration. And I see that v squared over r was simply equal to 7, so I can substitute that in. So acceleration is 4 times 7, or 28 meters per second squared. Don't need to round that to 2 sig figs either. And once again, I could do this with logic, thinking about the fact that acceleration is proportional to v squared. So if I double my velocity, my acceleration increases by a factor of 2 squared, or 4. Up next, we have a golf ball being swung in a circle on a string. So there is my string, and the golf ball is going in a circle, something like that. And we want to know when the ball is at the bottom of the circle here, we have the tension, we want to find the speed. So I'm, of course, going to start with my forces acting on the ball in this situation. We have the force of tension going up on the ball, and the force of gravity going down on the ball, and my acceleration, of course, is inward. Setting up my F equals ma in the y direction here, I'm going to have ft minus fg equals ma. My tension I know is 17 minus mg. That's going to be equal to m times v squared over r. And that just comes from the fact that centripetal acceleration, when we're moving in a circle, can be found with v squared over r. I substitute in for my mass, which is, be careful here, it's 0.6. I have 600 grams, which is 0.6 kilograms. So 0.6 times 9.8, and that's going to be equal to 0.6 times v squared over my radius, which is 1.6. Whatever the length of this rope is here, that's going to be the radius of my circle. So on that left side, I end up with 11.12, and that's going to be equal to, if I do 0.6 divided by 1.6, it ends up being 0.375 v squared. All right, so solving for v there, I end up getting that the velocity is 5.44 meters per second. Rounding to 2 sig figs is just 5.4. All right, so moving on to this next one, we have a person on a bike going around a curve at 13 meters per second. And we want to know what the coefficient of static friction is going to be between the tires and the ground. So I'm going to go ahead here and set up my forces acting on the bike in this case. So we're going to have the normal force going up. the force of gravity going down, and this is the side view here, so I'm thinking about the bike going around in a circle like that, where that's my center of the circle. So the other force I'm going to have, and the force that keeps it moving in a circle, is going to be the force of friction between the tires and the road. That's what makes it move in a circle in this case. My acceleration, of course, is going to be inwards towards the center of the circle, as it always is, in the direction of that unbalanced force provided by friction. So now I can go ahead and set up max and May. So in the y direction, I have the normal force and the force of gravity, so Fn minus Fg, and that's going to be equal to 0 because it's not accelerating vertically. So that means that my normal force is just going to be equal to mg. I don't know the mass of the bike in this case, so I'm just going to leave that like it is now. In the x direction, we have that force of friction, and that's going to be equal to m times my acceleration for an object moving in a circle, which is v squared over r, right? I always know that's my acceleration when I'm moving in a circle. I can now substitute in for Ff. It's going to be mu s times my normal force. We know that the force of friction is always less than or equal to mu s times my normal force, but I have this line here about the minimum possible coefficient of static friction. So if my mu is as small as possible, that means I need to use all of that frictional force. And so in this case, friction is at a maximum, and Ff just equals mu times my normal force. I can substitute in now for Fn, so mu s times mg equals m, and I know my velocity is 13, so 13 squared over 18. I can go ahead and cancel out the masses here, and I can solve for some of these numbers. So I have mu s times g, which is 9.8, is going to be equal to 13 squared over 18, which is 9.39. And so I can solve for mu, and I get that mu is 0.958. Answering to 2 sig figs here, that mu is just going to be 0.96. Moving on to this next one here, I have a situation where I have a puck going around in a circle on a frictionless table, and it's connected to a string, which is connected to a hanging mass, and that hanging mass is stationary. Okay, I'm told the hanging mass remains at rest. So what I'm going to do is I'm going to first set up my free body diagram, both for my puck and for that hanging mass. So for that hanging mass, I have the force of tension pulling up on it because it's connected to a rope, and the force of gravity, I'll call it Fg1, pulling down on it. For the puck, I'm once again going to use that side view and say it's going in a circle like this, where here's my center. Similar to what it is in that picture there. And so the force that I have on the puck, I have the normal force going up on it, the force of gravity, I'll call that Fg2, going down on it, and I have the force of tension from that rope. And that's that force creating that inward acceleration, okay, going towards the center of the circle. And my acceleration, of course, is inwards for the puck and 0 for the hanging object. So I'm going to set up my max and May here for both objects, starting with the hanging mass. So I have for that Ft minus Fg1 equals 0 because it's not accelerating. So Ft minus the mass of it, 1.2, times my acceleration, 9.8, equals 0. So my tension here is just going to be 11.76 newtons. For the other object, the puck, I really only care about my x direction because that's the direction it's accelerating, and there is no friction, so I don't need to find my normal force. So it's just going to be Ft equals m, and because it's traveling in a circle, I can substitute in v squared over r for my acceleration. My tension I just found, so I can plug that in, 11.76 equals 0.2 times v squared over 0.45. I can multiply by 0.45 and divide by 0.2, and so I get that 26.46 equals v squared. So my velocity here is just 5.14 meters per second. When I go ahead and round that to 2 sig figs here, I end up getting 5.1 meters per second for my velocity. For this next one, we have a car driving up over a hill, and the hill has a radius of 60 meters, so it looks something like that. It's a curved hill. And we have the car there at the top of the hill. So the car is going up and over the hill like that. We want to know the maximum speed the car can have without flying off the hill, flying off the road to the top of the hill. So let's start with our forces acting on the car in this case. We have the force of gravity going down. We also have our normal force going up. We are traveling in a circle here still. It's a little bit different than some of the situations we looked at, but going up and over that curve that is circular does count as traveling in a circle. So we're accelerating towards the center of the circle, which is down. So there's a really, really important line here, this without flying off the road at the top. Okay, so what I want you to think about for a second is what actually causes this car to accelerate in a circle while it's going up and over the hill? Well, in order to accelerate, we need that downward net force, which means that gravity must be greater than the normal force in this case, okay, to create that inward acceleration. And as we go faster and faster, okay, that acceleration is going to get bigger and bigger, v squared over r. And so that means that we need more and more force downward, more and more net force down. Well, gravity can't actually change, okay? Gravity is going to be the same. So how do we get more net force downwards? Instead of having a bigger downward force, we have a smaller and smaller normal force, okay? And as we go faster and faster, that normal force keeps getting smaller and smaller and smaller until eventually we have a normal force of 0. And that's the point where the car is going as fast as possible without flying over the road. If it was going faster than that, what would end up happening at the top is the car would be going, it'd be going, it'd be going, and it would just take off and actually leave the surface of the road because there'd be no more normal force and gravity wouldn't be enough to keep it moving in a circle. But there is a perfect speed where there is no normal force, and at the top of the hill, right at this point here, we have only gravity acting on it, keeping it moving in a circle. So that means that we actually only have one force acting on this object. So let's go ahead and set up our F equals ma based off of that. So we have the force of gravity equals our mass times v squared over r. Okay, substituting in for the acceleration of something moving in a circle, I'm going to substitute in mg for the force of gravity, and that means that I don't know my mass here, but they cancel, so I don't have to worry about that. So I can plug in some numbers. I have 9.8 is going to be equal to v squared over 60. So when I go ahead and solve this for v, I get that v is the square root of 588, or 24.2 meters per second. Rounding to 2 sig figs just leaves me with 24. Moving on to our next one, we have a conical pendulum here, which is similar to what we did in the Flying Pigs lab. We have an object going around in a circle on a string, okay, and the string is going to be out at an angle like that. And we want to answer a number of questions about this situation. So I'm going to start with my free body diagram here once again, showing the forces acting on this ball as it goes around in a circle. So in this case, we're going to have the force of gravity acting down on the object, and I'm going to say it's at this point here, which means we also have the force of tension from the string, but tension is going to be going up at an angle like that. Okay, we don't actually know our angle right now, but I'm going to define it to be that angle theta there. All right, I'm going to go ahead and draw my x and y components here. All right, so we're going to have ft cosine of theta and ft sine of theta are going to be those components. My acceleration, of course, is going to be inwards towards the center of the circle at that point. And now I can go ahead and set up my F equals ma in both the x and the y direction. So in the x direction, I just have that ft cosine of theta is equal to m, and my acceleration, because I'm traveling a circle, is going to be v squared over r, of course. And in the y direction, I'm going to have ft sine of theta minus mg, and that's just going to be equal to 0. So one useful thing to find here would probably be that angle, and we actually have enough information to be able to do that. So what I'm going to do is I'm going to go up here and look at the length of my strings here. So I know as it's going in a circle, okay, the radius of the circle is 0.2 meters, 20 centimeters, or 0.2 meters, and the length of the string, that hypotenuse there, is 1 meter. So I can go ahead and solve for that angle theta that I defined earlier. All right, this is the adjacent side of the triangle, that is the hypotenuse, so I can say cosine of that angle is equal to 0.2 over 1. And when I solve for theta there, I get that the angle is going to be equal to 78.4 degrees. Now that I have that angle, I can go ahead and use it over here in my max and my may. I'm still missing a number of things in my x, but I can go ahead and solve for some things using my y side. So I can say ft sine of 78.4 equals my mass, and I have a mass of 700 grams, which is going to be equal to 0.7 kilograms. And so I can say 0.7 times 9.8. And then I can go ahead and solve for my tension. So my tension in this case is going to be equal to 7 newtons. So there's my answer to my first question. What is the tension? So that's going to be 7 rounded to 2 sig figs would be 7.0 newtons. Now that I have that tension, I can actually go ahead and switch over to my x side. That gives me one more piece of information. And so we can probably solve for the velocity now. So I'm going to take this x equation here and start filling in what I know. I know my tension is 7 newtons. Cosine of my angle is 78.4, using those values we've already found. And that's going to be equal to my mass, which is 0.7 times v squared over 0.2. And then we can go ahead and solve for that velocity. So I take that left side, I'm going to divide by 0.7 and multiply by 0.2, and I end up getting 0.4 equals v squared. So when I take the square root of both sides, I get that my velocity is 0.63 meters per second. So there's my answer to part B. For the last one, we want to know what is the period of orbit of the object. And so for that part, I'm going to use the fact that my velocity is equal to 2 pi r over t. I just solved for my velocity, the 0.63, so that's equal to 2 pi times 0.2 all over t. So I end up getting 0.63 equals 1.257 over t. I would cross multiply here. I think that helps prevent mistakes. And we get 0.63 t equals 1.257. And we go ahead and solve for my time, for my period, and I end up getting 1.99 seconds. Rounded to 2 sig figs, it's just going to be 2.0 seconds. There's my answer to part C.